All right. So let's see. Today we're talking about threads, right? Is that what I mentioned? Probably, maybe. We're gonna make our rat move around. So, but on his own. Okay. So let me go here. All right. So we're gonna start off talking about something called interfaces. So an interface is kind of like a class, but rather than giving an actual implementation, the interface dictates what functions and implementing, I'm going to put that in quotes here, you'll see what that means in a second, and implementing implementing, that's a word, right? An implementing class must have. Okay, so to kind of think about this in real life, you know, you go into a grocery store or something like that, or really any store where there's the UPC codes on the side of the products, right? And they have like that little gun that scans the UPC codes. There's probably a bunch of different companies that make that a gun like that. That's UPC code compatible, right? All right. So inside that gun, that has to have a consistent. Some of the guns might do extra things than other ones. Maybe there's an advanced version that integrates in with their databases or something like that. But other ones might just be able to scan. But at the very least, all of those guns must be the UPC compatible. So they have to have implemented the bare minimum stuff for scanning UPC things. So we would say they have implemented the interface that is the, I don't know, by Java's definition, we would call this the UPC-able interface. And let me show you what I mean by that. If we go in, we'll look up something called Runnable Java. So Java has built into it a whole bunch of different interfaces. One of them here is called the Runnable Interface. And any class that implements the Runnable interface must write a single method, public void run. That's all it says. If you decide to write a class, so let's go ahead and just kind of see this by example. Is that us? That's not us. Let me just save that for right now. All right, so I'm going to create a test class here. And we'll say public class, test class. And we're going to say this guy implements Runnable. All right, I'm not going to put anything else in there. I'll just leave it blank for right now. All right, it says test class is not abstract, which it's not, and it does not override the abstract method called run, which Runnable dictates we must. Okay, Runnable does not have within it an actual implementation for a function called run. It just says you must write your own method and it must be called run. Okay, just like inside that UPC gun, there's got to be some sort of function where it's reading in consistent stuff where all guns read UPC codes the same way, at least for that initial information. Okay, so we would have to go in here and do something like public void run we don't actually have to implement anything here. and now it's happy with it. We just had to basically, we entered into a contract where we said, okay, you win, we'll write a run method. It doesn't say anything about what that run method has to do, just it policed us and said we had to write it. All right, that makes some sense? Okay. So, and actually what I'm going to do here. Well, so let me show you the thread class. Well, let me tell you what a thread is first. Okay, so that's what an interface is. And there's all sorts of different interfaces in Java that, you know, there's a collectible interface, I think, that all collections must have, things like that. So now we have something called a thread. Now, a thread is not a Java thing. A thread is a computer science thing, okay, kind of at the operating system level. So when a program first starts, it is running inside a single starting thread of execution. Historically, all running programs were represented as something called a process. All right, so you'll learn about this in the operating systems class, but I'll give you the 2-minute version of this. So every single time you double click a something on your computer, a process is born. All right, so your running operating system manages a collection of processes. Now, historically, if you wanted one process to be able to do more than one thing at once, you could have that one process spawn multiple sub-processes, child processes. And those child processes were every bit as powerful as the original parent. Now, the problem with this is, from an operating system perspective, one of the jobs of the operating system is to schedule for the CPU. So your CPU is this resource in your computer that's really, really, really fast. And it's easiest to explain this if we pretend like we don't have multi-core processors now. We just say we have a single processor with a single core. So technically it can only do one thing at once. What do we do then? What the operating system does is it says, okay, you have 10 processes that are all running. You have one CPU that can run one process at a time. We're going to have to come up with some way of feeding these processes into that CPU, giving one process a little bit of time on the CPU, kicking him out, let the other one come into the CPU, kicking him out, all with the ultimate purpose of faking the end user out. As long as the end user believes everything's happening at the same time because the processor is so fast, we're happy. Make some sense? All right, so that's let's say the job of an operating system. The problem with having a process create multiple child processes is all processes are treated equally by the operating system, which means if you have a program and you create 3 child processes for a total of 4 processes, now you're getting 4 times the amount of CPU time because the operating system is scheduling your logic, your 4 different processes, which are just maybe doing 4 different things that your program's supposed to do. Maybe you have a process that's making this rat run around and the process is making this other rat run around. And each one of those is getting extra CPU time that is unfair to other running processes on the computer. So that could be something that a programmer could take advantage of and say, well, you know, my program is always going to be getting 100% of the CPU time because I'll just create a zillion processes and just say, whoever currently has the CPU, you do some work. So we have this thing called a thread. And what a thread is, it behaves like a process. A lot of times these are called lightweight process. It is owned by a process, but shares in the CPU time that is allotted to the parent process. So now if you have a program and you create 4 child threads, that's great. Now you've created a situation, what's called a non-blocking situation, where you can have 4 things happening at once, seemingly, but you're only getting the same amount of total CPU time that you were given before. All right, you're not getting extra CPU time just because you have more child threads running around. All right, now in our modern day operating systems, where we do have processors with 4, 6, 8 cores, 16 logical cores, things like that, some threads do get their own CPU time because the operating systems have had to evolve and gotten smart enough to say, hey, CPU, you're not busy, work on this thread. The resource is there, we might as well use it. If we were just to generically say it, we would say that the job of the operating system is to try to keep the CPUs in the computer busy as close to 100% of the time as possible. Okay. At the end of the day, we only care as long as we're convinced that everything's happening at the same time. Okay. So we might say, generally speaking, threads are better than processes. They have a whole lot of advantages over processes, but that doesn't mean they're always the right tool for the job. As I mentioned, sometimes, depending on what problem you're actually solving, you will actually want to have multiple processes because you do want to have those additional time on the CPU, or you're forcing an issue where programs are running on 2 separate physical processors, something like that. So it's not that processes are dead. They still need to exist because they do house the original launch of a program. But a modern program, when it launches, a process is created and then it spins up a single thread and the program runs in that thread. So right now, when we start our program, 1 thread is happening and just everything is executing in that thread. Okay. So what I'm going to do here, let's go back to this guy. Stop this. Well, let's go look at the thread class here first. We'll see that the thread class implements the runnable. So this guy implements the runnable interface. And this is important for us. So now we know what interfaces are. We actually are not going to implement an interface directly yet. What we're going to do is we're going to extend a thread, and a thread implements that interface. But by default, a thread's run method does nothing, just like our current run method. And we'll talk about the role of the run method here in a second. So for all intents and purposes, a thread looks like that right now. If we were just to have this guy extend, we say this guy extends the thread class. Test class effectively is inheriting a run method that looks like that does nothing. Okay, probably not what we actually want. So we probably are going to want to override that run method with our own logic, things that we want to happen when that thread starts. But now there's more to meets the eye with a thread. Threads have several functions, but they have one magical function called start. This guy right here. So causes the thread to begin execution. The Java virtual machine calls the run method of this thread. Okay, so whatever is in that run method happens when we tell the thread to start. But this start method of a thread, this is the secret sauce for what we're going to be doing here. Because when we say start, magic happens behind the scenes where the Java virtual machine actually creates a new thread of execution. whatever it takes to do that. Something else that is sharing the CPU time with the fake processor of the Java virtual machine, which is then passing stuff off to the real processor on our computer. Okay, but it's doing that work for us. So we don't have to reinvent the wheel of how to create threads in the operating system. The thread class does that heavy lifting for us. All we have to do is tell a thread to start. We have to create something that is a thread. Then we write our own run method and put the stuff in the run method that we want to happen when that thread starts. Then we tell the thread to go. Make some sense? All right, so we're going to look at some examples today of why we might want to have threads. What problem does it allow us to solve? So just for the sake of argument here, I'm going to delete this class just because I want to name it something different. All right, we're going to go back to main here. And for right now, I'm just going to get rid of everything in main just so I effectively have a program that does nothing with a whole bunch of logic written. Okay, because all programs begin and end with main, and right now main's not doing anything. All right, so I'm going to go ahead and I'm going to create a scanner. So we're going to say a scanner input is equal to new scanner system.in. So we're going to read some stuff in from the user. All right, and I'm just going to do something forever here to drive this point home. And we're going to say system.out.println, enter a number. We'll do that as a print. And we'll say int number is equal to input dot. I'll write it I like to convert it myself, so I'll say integer dot parse int input dot next line. So it'll read it in as a string, and then I'll turn that string into an int. There's also something called input dot next int or next integer, one of the two. But in any case, I'll read in a number here from the user. And then what I want to do is I want to go ahead and let's just do something like for int I is equal to 0, I is less than number I plus plus, and we'll just go ahead and do a system.out.println. Something like count I, like that. Okay, now, so we'll go ahead and run this. I'll put in a 10. And then what we'll see it do is it'll display a 0, 1, a 2, a 3, a 4, a 5, yada, yada, yada. Enter number, I'll put in my 10. So there's my 0 through 9. Now it's asking me for another number. So what's happening here is this stuff right here has to complete before we ask the user for another number. Now let's put this into a real life example here. So we're going to say that this code blocks us from looping back up to do this again. Okay, just as this code right here blocks. If I start this program and I don't type in anything, we are sitting on this line right now, waiting for this guy to finish before I can ever get to this next line. So we would call this a blocking line of code. Now, in this case, we can't do anything until we have some user input. So blocking is okay. But sometimes we might want to have other things occurring while our program is maybe getting some user input. Good example would be, and maybe I've mentioned in here before, so how many of you use Google on a daily basis? Lots of people, right? Okay. And I suppose you're fed up with those long lines waiting in line for your turn to use the search engine. So when you go to Google's that website, you know, they say, oh, you're number 123 million in line. You know, please be patient. Thank you. Your wait time is 15 to 27 hours. You know, something like that, right? That doesn't happen, does it? So when you connect to Google, then what it does is it generates a thread. It's probably a little bit more complicated than that, since Google's probably running your stuff on a whole bunch of multiple servers on different regions and things like that. But for our argument here, we could say what happens is when the phone rings at Google and they pick it up, what they do is they spawn off a thread and hand that communication channel to that thread. Okay, so when you connect, this communication channel is now dealing with you, so that Google can now wait by the phone and get your incoming call. Gets the call, spawns off another thread that's dealing with you, so on and so forth. Okay, that makes it so that Google is constantly waiting by the phone, waiting for that incoming call, and only steps away from the phone long enough to spin up a thread and give it your communication channel that was coming in. All right, a lot of modern day systems, because it does take time to create threads, what they'll do is they'll pre-generate threads into something called a thread pool. So maybe they already have 100,000 threads just waiting to be handed work to do, something like that. Okay, doesn't really matter, but the problem we're trying to solve here is that you don't have to wait in line at Google, because that would be a terrible line. All right, now what do we do like at a McDonald's? They try to circumvent this. They have 2 or 3 registers open at once, right? Hopefully that the lines are now shorter, but you're still at the mercy of how many running threads there are at McDonald's. There's 3 registers open. There's 3 threads that can operate at the same time. Make sense? Okay. So what we want to do is we want to create a scenario here where maybe we enter in a number, and what we do is we hand off this stuff to the end user, so that they, or to a thread, so that they can communicate with that end user, while another user might want to do something else. So we want to take all this logic, and when we first come into the system, we want to say, okay, this guy right here is going to ask you for your number, then it's going to count to the screen, the number 1 through whatever you entered in. But we're going to wait for another user to come in, and they're going to ask you for a different number, and they're going to count to the screen that number, so on and so forth, so that this guy right here does not block us. All this logic will go inside of its own thread that will allow us to create another thread that asks somebody simultaneously for their number. Okay, so I'll just steal this code here. We're going to go ahead and create let's stop this, create a new class, and I like to call our first threads, I like to call worker bees. So we have a worker bee.java. So that's effectively what it's doing, right? We're offloading some work on this guy, and he's going to go in and do the stuff. All right, so we're going to say public class worker bee, and we're going to say this guy extends thread. So this worker bee is going to be a thread. It extends thread, and a thread implements runnable. But now for our worker bee to actually be effective, we need to write our public void run method, because the one that came with thread does nothing. We want this guy to create a scanner and then forever ask the user for some information, and then spin through and count and things like that. Okay, now just to kind of prove our point here, I'm going to make our constructor for worker bee. Because worker bee is a normal class that just happens to be a thread. So we're going to say that a worker bee is going to keep track of their name. And we'll say this dot name is equal to whatever name was passed in. So when we first create an instance of worker bee, we will name him. your B1, B2, B3, so on and so forth. Or, you know, if you want to get creative, you can name your bees whatever you want. All right, but they're going to have a name so that down here we can do something like let's do it this way. We'll just preface our enter a number with whatever the name of this bee is, so we know who's asking us for a number, because we're going to be experiencing all these different threads in the same window. So it'll be helpful for us to see who's actually talking to us. All right, similarly, when we output stuff, we'll also put the bee's name before it. Okay. So when we create a worker bee, we give it a name, and then its run method creates a scanner, and forever it's asks the question, putting something out in front, and reads it in. We saw earlier that this line does block, and then it just does some counting and asks them the question again. That's all a worker bee does right now. So we're going to go back to main. And why don't we just create 3 bees? We're probably going to need our java.util.scanner over in worker bee. Otherwise, I won't know what a scanner is. So we're going to do something 3 times. What are we going to do? We're going to say worker bee WB equal to a new worker bee. And we're going to call this guy B concatenated with an I, so it'll be B0, B1, B2. And then we're going to tell our worker bee to start. All right, so the parent is going to immediately, so our original thread, main, all programs begin and end with main. The parent's going to immediately go in and spin up 3 threads. And each one of those threads is going to be talking to whoever's sitting at the keyboard. So they're all going to be talking to me in this case. But if you think about this as like a network type thing, you know, they're talking to you at your computer and you at your computer and so on and so forth. We just happen to be looking at it through one window, which is why I'm naming them. All right, so we're going to create 3 worker bees and tell each one to start. When we tell the worker bee to start, it does its magic behind the scenes of whatever it takes to create a new thread. And then ultimately it calls the run method. So each of those bees will say, hey, I'm B0, enter a number. You'll enter in the number and then it'll do the other things. We know for a fact that we've seen this line block, this line blocks. This input.next line waits until we actually type in something and press enter. So notice here, I probably need to, well, because my prompts are, I don't press enter, I do system.out.print, enter a number. So you see there, all 3 bees have prompted me. Just gonna make it a little bit funky. Who am I answering first here in their terminal? So here, let's do a 10. Well, it's not gonna let me take over the same terminal here. It's an unfortunate example, I guess. We'll do 20, we'll do 40. All right, so the bees only blocked each other because I was entering it all in from the same terminal. Those things were happening separately. And now we can kind of see that B1 started his count, then we see B2's getting some CPU time in there, B0, B2, B0 gets a bunch of CPU time, Then we got some alternating back and forth, B2, B1, B2, yada, yada, yada. And now we're back to B2. Oh, so actually B0 has not finished yet. Oh, he's asking me for a number up here. So B0 asked me for a number here. This thing kept running. So this is going to be entering the number for B0, then B2, then B1. So on and so forth. All right, that makes some sense. If we don't want to have the user input there, so we can just kind of see how this works, maybe a little bit cleaner without the IO. I'll just stop this. I'll do a random number generator in here. Rather than ask the user for a number, we'll just do r dot next int, and we'll mod this guy by 200,000. So that'd be a number between 0 and 199,999. We're doing this forever anyway, so these guys are just going to keep counting, flipping back and forth. So forever, we're going to be just counting. So I'll go back to main here. We spin up 3 different Bs. They all start doing their counting. And we kind of see them flipping back and forth between which B is currently getting CPU time. Oh, no way for me to look at it after the fact. Whatever. All right. So kind of see how that's working. So now how do we want to apply this to our game? Well, what we want to do is we want to have each one of our monsters to have a brain of their own. That is, each one of our monsters will be a thread. Okay, where we can tell a monster to start going. Now, we could do it that way. We could say a thread is a monster, or we can have kind of like we can think of it like almost like a segue type thing where, you know, we have another class that drags monsters around. Think of it like that. But let's give monsters a thought. I think we originally had said that players are controlled by human beings and monsters are controlled by themselves. But right now, a monster is effectively like a stuffed bear that the player has to pick up and throw through an exit, right? So we want to give this guy now its own brain. So we're going to go into monster. And we're going to say that monsters, they extend inhabitant. And they also, let's actually go this route. Say a monster is an inhabitant. So right now we haven't made monsters anything special. Okay, so what we're going to do, we want only the monster type to be a thread, but we can only have him extend one thing. A monster is an inhabitant, as we have it written right now. And I don't think we want to change that. So we really need to create another level beyond monster, maybe called mobile monster, something like that. So we'll call this guy a mobile monster. And we're going to say a mobile monster we gotta have this. One of these guys has to be a thread. I don't think mobile monster is going to be what we want either. That's okay. We'll do it this way. I'm going to get rid of mobile monster. This will make it easier anyways, I think. We're going to modify inhabitant. We're going to say that inhabitants extends thread. So all inhabitants are threads, which means they have a start method, and that if we want them to do something special, we probably need to write our own run method, especially if we're going to say we want to start them. Now, for us here, right now, we have a player, and this kind of goes back to somebody asked a couple classes ago, well, what if we're going to have multiple players? Well, if you're going to have multiple players, then you're going to have multiple incoming connections to this MUD server. Each one of them is going to have a communication channel with their own keyboard attached to it and stuff like that. So at that point in time, we probably would have a player be a thread as well, where we'd say, okay, you're a player, no problem, spawn off a thread. Since you're a player, this is what you do when you're running. And we'd have 5 or 6 active players in our MUD at a time. We'll have 20 rats running around, whatever it is. But each one of them is running in their own thread because we don't want one player to have to wait for another player to finish typing in their command. Right now, we have a single player situation. So we're actually not going to implement this on the player side, but we're going to say all inhabitants are threads. And threads are objects, which implement runnable. So now for monster, we're going to go ahead and we're going to write a public void run method here. And this run method is going to, I don't know, ultimately is we're going to want the monster to kind of move around at some kind of random clip, right? Let me look at thread real quick. I think there's a wait. Here, we got to sleep for some number of milliseconds. We'll do that. All right, so we'll just say, until it's brain dead, all monsters are just, they do something forever. And what are they going to do? They're going to go ahead, we're going to say sleep 2000 milliseconds. That's 2 seconds. The rat's gonna say woof. All right. So when we tell a rat to start, forever, the rat is going to, every 2 seconds, just speak up and say woof. Okay, mind of its own. So let's go back to main here. Let me get rid of my, well, I'll leave the worker bee class there as just our example. All right. So we've already added the player. We've added the rat. We're going to go ahead and tell the rat to start. The rat's a thread. So we just kind of hit the on button. We threw you into the room and now we hit the on button. Every 2 seconds, the thread's going to start babbling. Oh, a thread. A thread has a name. It's what it's saying is we can't override get name. We weren't intending to override get name, but thread has a method called get name that we're not allowed to override because it must be used by something else. So we'll just say get inhabitant name, and I'm gonna steal that here because we're gonna have several. I'll just let it show us the errors where we've used get name in our program, and I'll just copy and paste this. Okay, so this is an exception. We talked about exceptions last class. It says that this could cause a problem, so we have to try to do it and then possibly throw the exception. So inside monster, the sleep command here possibly could cause a problem. So we will try to sleep and then say something. Technically, only the sleep needs to be in here, but we'll put them both in here. And then we'll catch exception-y and not do anything. Actually, I'll do this. Problem with sleep. I don't expect we're going to ever see that, but that just lets us know that's what that is catching. Some issue with the sleep command. So there's after 2 seconds. 1, 2, 1, 2, 1, 2. It's every 2 seconds. And I could still, I can go north. So now I've moved to the next room. Now what's going to be funny here is even though we're in a different room, because the rat is writing out to system.out, we're still seeing it since everything's writing out. So even though we still hear the rat woofing in the next room over. Okay, but hopefully we're seeing here that the rat has a mind of its own, right? It's off doing its thing, and the player can still move around and stuff. Screens get a little crowded, but it's certainly working. What's up? I can. It's exit, I think, right? But hold on, that thread is still living. Yeah. So, what do you want me to do? Well, and you also here changing it to just thread. Oh, that's because of the get name. Yeah. So a few minutes ago I said, oh, I'll just let it tell me when I had an error. Well, it's not going to tell me I had an error because thread gives it a get name function. The name of the thread is thread 0. So I probably need to go through and search for the get names in my code and change it to get inhabitant name. So it reads in rat, not whatever the thread name is. Make some sense. All right. Questions about threads? Go ahead. Well, you would probably, so when we exit out of that, let's just see how this is ending. When I exit out of play here, it really does end. I actually would have expected the rat to have stopped because the thread is owned by this class. So when the play method ends down here, yeah, but I never started the thread. So yeah, it's yeah. Ask that at the beginning of next class, or ask it on Slack and I can look at it over the thing. But I would have expected the rat to have died off. The rat should die as soon as the program ends, because the thread is owned by the program. It's not a separate entity running amok on the operating system. Okay, questions, comments, concerns, bribes. All right, I'll see everybody on Monday, we'll start implementing our wrap moving around in a thread. I'll also talk about the midterm. Midterm's going to be next Wednesday, and then I'll grade it and we'll go over it on Friday. Which part? Oh, the code? Yep.